Alrighty, y'all. Today we're taking a look at the recitation for February 9th. And for this one, we're going to be looking at describing 2D motion with X and Y components. Right? So question 1, we have a hiker crossing a stream. Right? We have some information about the stream, about our initial trajectory, and all this other stuff, right? So the first thing we're going to do is draw a diagram and pick a coordinate system, right? So I'm going to draw our stream, right? I'll put some water in the stream, why not, right? And here's where our person's starting, right? They're going to be throwing their boot up and over, kind of like that, so it lands on the other side. Here's going to be our 12 meters, and I'm going to say this side is 0, right, where we're starting from, and this is 12 meters, right? And we have to set the same thing in X and Y, right? This is going to be 0, and our positive Y is going to be going up, right? This is going to the right. Right, and this is, right, here's our initial velocity, tangent to that, and here's horizontal, there's our 35 degrees, right? Right, and I'm just setting my 0 as here because it's been easy thus far to have, in terms of thinking about it, to have our starting point be 0, 0, but you could set it opposite, you could have it backwards. Really doesn't matter as long as you set which way is positive, I'm saying up and to the right, and keep it consistent through the problem, right? So now we know our initial velocity vector is, right, as a magnitude. We're trying to find our magnitude, but we have our direction already. Right, so, but it's easier to work with our X and Y components when we're looking at our kinematics in each direction, right? So let's start doing some trig for this. So here's our V naught, right? And here's our horizontal with our, I'm just going to keep it as theta for right now, but it was given in the problem, right? At 35 degrees. Okay, so here's our X direction, and now here's our Y direction. V naught Y, V naught X. Now let's do some trig, right? So we have sine of this angle, right? Sine theta is opposite V naught Y, opposite over hypotenuse, over V naught, right? And we're trying to solve for V naught Y, that looks like a 6, V naught Y in terms of V naught and sine theta, right? So if we multiply both sides by V naught, we get V naught Y is V naught sine theta. We follow a similar thing when we're solving for our V naught X. It's going to be cosine is adjacent over hypotenuse, and we multiply by the hypotenuse. We're going to get V naught X is V naught cosine theta. Right? So now we have that in terms of things we're solving for and things that we know. Right? Now we're going to write our kinematics equations. I'm going to kind of combine 3 and 4 for just because I don't have space to write on it right now. But, oh look, our kinematics equations are already written for us. It's almost like I planned ahead, right? So let's think about what we know for each of these equations, right? So we know in our X direction, right? We don't know our V naught X yet. That's what we're trying to figure out, right? Vx of t. V naught X, right? We just said that's going to be V naught cos theta, right? And our acceleration in the X is going to be 0, right? Because we're only accelerating from gravity. That's only in the Y direction, right? So our equation, first kinematic equation, V naught cos theta. That's all it is, right? Simplify that down. And I'm just going to move it over so now I have space to write down, right? Now our X position as a function of time, right? We said that our X naught, our starting X, was going to be 0, or I said that, and you all agreed because I said it, right? Our V naught X, again, was our V naught cos theta, right? Times time, plus, and again, our acceleration goes to 0, which means all of that goes to 0, right? So that means X is a function of time is V naught, and I'm going to just move the time in front of the thing as well, cos theta, time times cos theta. Wonderful. Now we go on to what's a little bit more complicated, but It's fine. Believe me, we'll do great, right? Y is a function of time. Right? Our y naught, again, is 0, right? Because we set that in our setting our coordinate system. Plus, we said v naught y is going to be v naught sine theta. Wait, did I write that right? Yeah, it's cosine theta for x, sine theta for y for this one. Times time, plus, and then our acceleration, our y, right, because we have gravity, and we have 1/2. And since I said down is going to be negative, this is going to be a negative g t squared, right? Now just simplifying that, y of t is v naught, and then I'm just going to move the t in front again, just for my ease of reading. It's going to be minus g over 2 t squared. Wonderful. Now finally, vy is a function of time, right? We said our v naught y, again, v naught sine theta, plus, and we said, again, our ay still in the negative direction, negative g. Right, so our vy is going to be v naught sine theta minus gt. Cool, so we have some equations. Now we can start looking at the actual problem, right? So really for this problem, we're going to set up a sentence. And, right, so this frame of our sentence is going to be, what is value of blank so that blank is true at the time when blank is also true. All right, so this is going to be how we're phrasing our question for what we're answering, right? So what is the value of blank is always going to be, what is the question asking for, right? So our question's asking, with what initial velocity, right? What is the value of v naught, right? And now we have to consider, so that, right, what do we want to be true at the end of our thing, right? So what velocity must you throw the boot in order to get it across the stream? So what has to be true with our v naught, right? So if we look, right, we're landing over here. What's going to be true is our x is going to equal 12, and our y is going to equal 0 again, right? So what is the value of v naught so that y equals 0 at the time when x equals 12, right? All right, sorry, I'm going to flip these just for ease later. It doesn't really matter. All we really need to know is that these are going to be happening at the same time, right? Y of t equals 0 when, at the time when x of t equals 0, and this is going to be an initial condition that gives us these final conditions, right? So now we use our equations, right? So we're going to get, I'm just going to pull these down, right? We have our initial equations. And now let's solve for the time when y equals 0, right? So we're going to set y of t equal to 0 equals v naught t sine theta minus g over 2 t squared, right? It's a quadratic, and we set it equal to 0, so I'm going to factor out this t, right? Equals t, parentheses, v naught sine theta minus g over 2t, right? And, right, we're going to get two answers for t. We're going to get t equals 0 and t equals something else, right? And we know that our y is going to be 0 when t equals 0 because we said that was going to be true, right? We said that our initial y, when time is 0, y naught is going to be 0, right? So that makes sense, right? There's a quick sanity check on that, right? So now I'm going to set this other part equal to 0, v naught sine theta minus g over 2t equals 0, right? Because that's how we solve our quadratic. And now I'm going to solve this for t, right? So I'm going to move this to the other side. V naught sine theta equals g over 2t, and then I'm going to divide both sides. We'll multiply by 2, divide by g, right? So it's going to be 2 v naught sine theta over g equals t. Cool. Now we have the time when y equals 0. Wonderful. So we're going to plug this time into our x equation, right? X of t equals v naught times 2v naught sine theta over g times cosine theta, right? I'm just going to simplify this real quick, right? X of t equals 2 v naught times v naught is going to give us v naught squared, sine theta, cosine theta all over g. Right? Cool. So now we have something, right? So but that's not the only thing we wanted true. We already have that our y of t is going to equal 0. Right? But this means that we could be landing at any point along here, right? That's just finding when our y of t equals 0. Now we have to set our condition that x is going to equal 12, right? So we're going to say 12 equals 2 v naught squared sine theta cosine theta over g, right? And now, right, we have one equation. It looks like we have two unknowns, right? Theta I just haven't plugged in just yet, right? But we were given theta in the problem, right? Our initial direction, right? And remember, this theta, that's our initial direction of our v naught vector. That's our direction of our initial velocity vector, right? That's not the direction of our position vector, right? Right, so we know theta, but we don't know this, and we know g, right? Because g is just our 9.8. We have one equation, one unknown. I'm going to solve for v naught, right? So it's going to be 12g. I'm going to divide by 2, so it's going to be 6g over sine theta cosine theta, right? And we're going to take the square root of that. That's going to give us our v naught, right? And I got v naught to be roughly 11.1869257, and that's in meters per second, right? Because we're at velocity, and I got everything into base units. Do not use this many decimals. It's a me thing. You should round and keep to a normal number of sig figs, right? Now, we have that she accidentally throws the second boot for the same v naught that we just calculated, but an angle 65 now instead, right? So we know, now we're looking at, right, if we have this v naught and this angle, right, we're trying to find where it lands, right? So again, what is the value of blank at the time when blank equals blank, right? So where it will land, what is the value of where it will land? That's going to be what's our value of x at the time when, right? How do we know that we're landed? How do we know this final condition has been met, right? As I was saying before, we know we've landed when y equals 0, right? We had to set the second condition, right, that we wanted it to be going this far. But we know that we've landed when y equals 0, right? So what is the value of x when y equals 0, given these new initial conditions, right? We know this is staying the same. Our v naught's going to stay the same, but we have a new angle that we're throwing at. So we're going to revisit all of our trigging, right? So for this one, we're going to just pull these equations again, right? Because our equations haven't changed because I left everything in terms of theta, right? So really it would just switch our theta into, instead of being 35, it would be 65, right? So let's find the time when y equals 0, right? So it's the same thing that we just did, right? So I'm actually just going to pull the work from up here, right? We set it equal to 0, factor it out. Nothing has changed. Our acceleration is still the same in the y direction. The only thing that's different is this theta, and now we know this v naught, right? We now know v naught, so we can, when we plug in, we can find that. But now when we plug this t, right, this is when y equals 0. This is our time when y equals 0. We plug this into over here, right? Same thing we did, and it's all simplified for us. Wonderful, right? Now instead of plugging in 12 for this, we don't know where it's going to land, but we do know this initial velocity, right? So we know our theta, we know our g, we know our v naught. We have one equation, one unknown, and we can solve this, right? So if we plug in our like 11 point, whatever it was, 187 squared, and it's going to be sine 65 cosine 65 over 9.8. That's going to give us some value of x, right? And when I punch that into my calculator, right, I'm going to get that our x at the time when, right, at the time when y equals 0, our x is going to equal around 9.7824896222 meters. Right? And again, units, very important. I kept everything in base units, so that's going to be our final answer for where the boot lands the second time around. Alrighty. Now we go on to question 2, right? So we have another scenario, right? We're throwing snowballs off of a building, right? So we're going to draw a quick cartoon of our problem, right? Alright, here's our building. I'm going to make it shorter for ease of drawing. Right, here's our building. And here's our person down on the quad that we're throwing things at. Right. And, right, so we're throwing the snowballs with some initial velocity. We're given that that's v naught. Alright, and we're at some initial theta. Alright, here's our v naught. There's our some theta. And there's, alright, now we have to set a coordinate system, right? And I'm going to say that, right, here's our building. Right, we know that it's a height of h. Right, so we don't have any numbers for this problem at all. We're just going to be doing all with symbols. Right, so there's our height h. So I'm going to say that our 0 is actually down here, and our h is up here. Right, that's going to be a positive direction. Right, I'm choosing to set that as positive. We could set this as 0 and this is h and say that this is positive for this one. And it doesn't matter, you get out the same results, but you just have to clarify, right? As long as you set your coordinate system and keep it consistent, right? That's all, like, you'll get the same results as long as, and they'll be grounded in your coordinate system, right? And I'm going to say that this is 0 and going this way is going to be our positive x, right? It's easier. Wow, what a coincidence that our kinematic equations are already written for us down here, right? So now let's substitute in some things that we know, right? Same thing we did last time, right? Our x of t, right? Our x naught, right? I just said, the way I said it, our x naught's going to be 0, right? So that's 0 plus, we're going to do our same trig for this, so I'm going to move the vector over here real quick, right? There's our that. Here's our theta, here's our v naught x, v naught y. All right, we set up the triangle in the same way, and I kept everything in terms of theta up here. So we're going to end up with the same v naught x and v naught y. So this is going to be v naught cos theta t plus, and again, our acceleration in the x direction, because we're going to be in free fall, it's going to be 0, right? Now we say our Vx of t, same thing, right? Our v naught cos theta, and our acceleration is going to be 0. I'm actually going to simplify these equations too. X of t is going to equal v naught cos theta t, and then it's going to be Vx is going to be just v naught cos theta, right? Because our x velocity isn't going to be dependent on time, because our x velocity isn't changing because we're not accelerating in the x direction, right? So that makes sense that that's what it looks like, right? Sanity check, you know. Now our y of t, right? Our y naught, I said that I'm starting from up here, so my y naught is actually going to be h for this one, right? It's not going to be 0 like we've usually been setting it. That's just how I set it up. You can have it be 0, but then you have to remember that your initial y velocity, if you're saying this is 0 and this way's positive, our initial y velocity is going to be going up, so that's going to be a negative direction. We're going to be accelerating down, which means that's now a positive direction. I'm not doing that. I'm going to keep the coordinate system up is positive, right is positive, right? Which means that I'm going to have a v0 sine theta times time, right, plus our 1/2. Again, our acceleration, it's gravity, and I said that down is negative, so it's going to be a negative g t squared. Okay, and I'm going to just move this over a little bit so I have room for the last one, right, which is our vy is going to be, again, our v0 y, v0 sine theta, plus our acceleration, again, negative g times t. So that's going to be vy t is v0 sine theta minus gt. Right, I'm just going to rewrite this one as well. I of t is going to be h plus v0 sine theta t minus g over 2 t squared. Right, that's just smishing this together, so that's our negative there. Cool. Put in everything we know. Now we can start thinking about what the problem is actually asking. So now we're writing sentences. Right? This is a very important part to make sure that we're understanding what we're being asked and how we know we got there. How do we know what we're doing, right? So how much time does it take for the snowballs to hit the quad, right? What is the value of blank when blank is true, right? This is essentially our phrase for a lot of our stuff, right? What is the value of blank when blank is true? Ooh. I meant to copy that, not duplicate it. Sorry. What is the value, right? So how much time does it take for the snowballs to hit the quad, right? So what is the value of time is what the question is asking for. How much time, right? What is the value of t when what is true? How do we know that we have hit the quad? How do we know that we have gotten to our end result, right? When we're hit the quad, right, we go up there, we hit, and we're hitting the quad down here. The thing that we know is going to be true, we don't know our x position, we don't know anything else, but we know that y is going to equal 0. The way I set up my coordinates, y equals 0, right? So what is the value of time when yt equals 0, right? Now, where do the snowballs land on the quad, right? This is going to be something similar. What is the value of blank when blank is true, right? Where do the snowballs land, right? This time we are trying to find, right? I said we didn't know our x position when it lands. That's what we're going to try to find, right? What is the value of x of t, right? Our where do the snowballs land when what is true, right? So I'm actually going to switch this and say at the time when what has to be true. Right? It's our same final condition. Right? Our same final condition, right? When it's hitting the quad, landing on the quad, right? So we know that y of t is going to equal 0, right? That is our final condition. We know they're landing on the quad, our y of t equals 0. So what's the value of x of t at the time when y of t equals 0, right? And how fast are the snowballs traveling when they hit the quad, right? Right? So again, so we're trying to find, right? This is what we're finding, and this is how we know we've gotten there, right? How fast are the snowballs traveling, right? So how fast, right? We're thinking velocity, right? But it's asking just how fast are they traveling. It's not specifying a direction. So this is going to be our speed, right? And our speed is our magnitude of the velocity vector. So I'm going to say, what is the magnitude of the velocity vector at the time when, and again, how do we know we've hit the quad? Y of t equals 0, right? in what direction are they moving when they land on the quad, right? Again, we're landing on the quad again, right? So we're going to have something similar. Or we can keep our y of t equals 0, right? Because that's our final condition. We're landing on the quad, so it's going to be what we're looking for at the time when y of t equals 0, right? So in what direction are they moving, right? That's going to be the direction of our final velocity vector. What is the direction of the velocity vector? Right? But which velocity vector, right? Because right now we have Vx and Vy, right? So if we solve for Vx and we solve for Vy, right, we're looking for our total direction that we're moving, right? Because our velocity in the x direction is just going to give us how fast we're moving this way. There's our direction for that vector. Our y velocity is just going to give us how fast we're moving this way. There's our direction for that vector, right? So we have to add them together, right? So this is going to be the total velocity vector, right? So this is going to be, right, if we remember our Pythagorean theorem, not V naught, Vx squared plus V naught, not V naught, oh my goodness, squared, and we square root that, and that's going to give us our final velocity as a function of time, right? We're trying to find the direction of this, right? This one gives us the magnitude, so this one should be up here, right? And our direction, that's going to be like what angle it's making, what angle it's going to, that triangle is going to make, however you set up your triangle, right? Cool. That makes sense. All right. So now we're throwing snowballs back up on top of the building. All right. So I'm going to steal my drawing from before and just modify it a bit. All right. So I don't have to redraw almost everything, right? So now we're throwing our snowballs from the ground up towards the building, right? So here's our, now, right, here's our V naught. Here's our theta, right? And we're going to be throwing them kind of so they arc up, right? And hit the wall, right? And we know now that we know our x, right? We're going to be a distance d, right? It says a distance d away from the building, right? So I'm going to keep my coordinates the same, and I'm going to say that this is still my 0, this is still my h, this is still my 0, and this is still my d, right? But, all right, we have to remember that our coordinates now, if I'm saying that this is positive and this is positive, all right, I have to remember that some of my stuff is now going to be negative in reference to these coordinates, right? So, all right, and we're going to have a starting x. We're going to have an x naught as well, right? So let's start plugging in some things to what we know to our kinematics equations, right? X of t equals, I just said we're going to have an x naught this time, right? We're starting at a distance d away from what I said was 0, right? So our x naught's going to be d, right, plus, right? We have to set up our triangle again, right? This time our triangle's going this way. Here's our theta, right? Here's our v naught. We're pretending that's a clean right angle because I can draw. V naught y, v naught x, right? It's still going to be v naught x is going to be v naught cosine theta for the magnitude, but now, right, I said positive was to the right. Our v naught x is starting by pointing to the left, so now this is going to be a negative, right? And our v naught y is still going to be positive, right, because that's the way I've set up the axes, right? This is still going to be positive, right? So you just remember that, and we come back over here, right? So our negative v naught cosine theta times time, right? And nothing has changed for our x acceleration, right? Because our x acceleration is still going to be 0 because we're still only accelerating because of gravity, right? So we're going to say x of t equals d minus v naught cos theta times time. Cool. Now let's get our x velocity, right? Vx of t, same thing we just said, negative v naught cos theta plus our 0 acceleration. Right, so Vx of t is going to equal negative V naught cos theta. Cool. Now our y of t, right? Again, this is where we start having some acceleration, right? Before we had our initial height, our initial y. I'm going to draw a person standing up here, right? Because we have our friend up here, right? Before we had initial y because we were starting at h, but now we're starting at the ground again and throwing the snowball up towards the building. All right, so now our initial y is going to be 0 again, right? Plus, and we said this was V naught sine theta t plus 1/2, right? And our acceleration, right? I said up was positive, so our gravity going down is going to be a negative g t squared, right? So simplifying this, it's going to be V naught sine theta times time minus g over 2 t squared. Cool. Now finally, Vy of t, right? So the same thing, V naught sine theta, right? And again, our acceleration is going to be negative g t, right? So just rewriting that, V naught sine theta minus gt. Cool. Got all of our equations. We got through it, right? So now let's write a sentence in terms of our variables that will let us figure out how far above the ground the snowball hits the side of the building, right? So we know, right, the first thing that happens, right, snowball slips out of his hand and it hits the side of the building without making it all the way up, right? That's what I was drawing here. So, right, how far above the ground the snowball hits the building, right? So what is the value of blank at the time when blank is true, right? So we're asking for how far above the ground the snowball hits the side of the building, right? That's going to be like this distance, right? So that's going to be our value. What the question's asking for is our value of y, right? Y of t, right? At the time when, right? Now let's figure out how do we know that we've gotten there? What is true on when we're hitting this side of this building, right? We don't know our y coordinates. We're figuring that out. We're not going to know our velocity right away, right? But we do know that our x, because I said that here was x equals 0, at the time when x is going to equal 0, right? So when x equals 0, right, when our snowball reaches this kind of plane, right, what is its height at that point, right? What is the value of y of t at the time when x of t equals 0? Cool. All right, so now we have a sentence and we have some equations. Let's get answering, right? I'm going to pull my equations down here, right? How far above the ground the snowball hits the building, right? So we're trying to find y of t at the time when x of t equals 0. So let's start by finding the time when x of t equals 0, right? So we set this equal to 0 equals d minus v naught cos theta times time, right? We're trying to solve for time because we're finding the time when x equals 0. Right, so I'm going to bump this to the other side. We're going to get v naught cos theta times time equals d, right? Dividing both sides, so it's going to be t equals d over v naught cos theta. Wonderful, right? Time when x equals 0. Now we're trying to find our y of t at that time, right? So we're going to plug this into over here, right? So y of t, right? And it's going to be v naught sine theta times our d over v naught cos theta, right? Because there's our time minus g over 2. There's our d over v naught cos theta, and that's our time squared, right? Just move this down and away from the other equations real quick, right? So I'm going to simplify this, right? This one we simplify, it's kind of messy, right? So it's going to be v naught divided by v naught because it's multiplied, so that's going to cancel out. sine over cosine is tangent, right? So yt equals d tan theta minus, and we're going to be squaring this, and so it's going to be g d squared over 2 v naught squared cosine squared theta, right? And hypothetically, given in the problem, we don't have numbers to plug in, but if we were given d, we were given theta, we know g, we were given d again, right? We know our v naught, we know everything in this equation. If we plugged in numbers, we would be solving for our y of t, right? That's what our question's asking for at the time when x of t equals 0, right? This is going to be our answer for this one, right? So he throws another snowball, again, an angle theta, right? But this one is thrown harder, right? And it hits the feet, right? So this one, instead of hitting low, it's going to kind of arc up and hit our feet like that, right at our feet there. Write a sentence in terms of algebraic variables that figure out how fast he had to throw it, right? So this one, what is the value, this one, right? What is the blank, right? We want to find some initial condition, right? How fast he had to throw it initially so that two things are true at the same time, at the time when blank is true, all right? So we're trying to find out how fast, right? So that's going to be the magnitude of the velocity vector. So what is the magnitude of v naught so that two things are true, right? And we're given the angle that it's at, so we already know the direction of v naught, so we're just going to find the magnitude, right? That's our how fast, that's our speed, all right? So what is the magnitude of v naught so that blank is true at the time when blank is true, right? So how do we know that we've achieved our goal, right? Right, we've hit right here. I already said when we're hitting the building, our x of t is going to equal 0, right? But now we also want another condition to be true, that we want our y of t to equal h at that same time, right? So that x of t equals 0. We're going to put that we want y of t to equal h at the time when x of t equals 0, right? At the time when we're hitting the building, we want our height to be just this high, so it's hitting the feet, right? So I'm going to do the same thing that I did before, right? Let me grab my equations, right? Duplicate that, bring it down, right? So now, right, it's the same thing, right? The first thing we're going to do is find the time when x equals 0, right? So I already did that, set x equals 0, solve for time. So I'm just going to pull this answer down. Oh, I pulled too much. It's fine, right? Right, so that's we solved for t when x of t equals 0, right? And now we're going to plug this into our y of t equation, right? The same thing that we just did. We're going to plug it in and simplify it, right? So when it simplifies down to this. But now, instead of this being our answer, we're solving for y of t. Now we don't know this v naught. This is what we're solving for, right? So now we plug in h, for y of t, right? Because that's our other condition. So we're going to do h equals d tan theta minus gd squared over 2 v naught squared cos squared theta, right? And now we solve this monstrosity for v naught, right? So I'm going to do some finagling and get some things to the same side. So it's going to be gd squared over 2 v naught squared cosine squared theta. It's going to equal d tan theta minus h. right? I just bumped this to the other side and then got rid of the negative for both, so I had to flip the signs for these. All right, and now I'm going to multiply both sides by v naught and divide by this, right? So it's going to give us gd squared over 2 d tan theta minus h cosine squared theta, all right? It's going to equal v naught squared, and we're going to take the square root of both sides. And that's going to give us our final answer for our v naught. How fast, right? The magnitude of v naught, we already have the direction. So this is the magnitude of v naught so that these two things are true, right? All right. So this was this recitation, right? An intro to 2D motion. Let me know if you have any more questions about this or any other questions that you want me to try to explain, and I will do my best to try to explain them because I guess Sydney explains stuff.